Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are beginning a deep dive into Chapter 12, Atoms, focusing on the basic introduction. Our mission is to make this complex topic so clear, so simple, that you will lose all fear of it and remember the core concepts for your exams. Okay, so let's start with something you see every day. A very simple observation. You've seen neon signs, right? They glow with that very specific, very bright red color.
Oh, yes, all the time.
Or think about a chemistry lab. If you accidentally spill some common salt sodium chloride into a Bunsen burner flame, what happens?
It instantly flashes that bright, vivid yellow. I've seen that. And it's not just salt. Copper compounds, they always make this distinct blue-green flame.
Exactly. It's like each element has its own signature color.
Yes, no matter how you heat it.
And that right there is the mystery.
Yeah.
That's the hook. Our first intuition, our classical thinking, might suggest that the color should depend only on how hot the flame is. Hotter means whiter, cooler means redder, something like that.
But you're saying it's not the temperature. It's the element itself that decides the color.
That is precisely the point. This simple fact tells us something profound is happening. Something inside the atom is responsible for these unique colors. These colors are like an atomic fingerprint. And classical physics, for all its successes, had absolutely no explanation for this. It was a complete failure. So let's get to the core idea. We now know an atom has a tiny, dense, positive nucleus at the center, with electrons surrounding it. But the revolutionary idea, the one that changes everything, is quantization.
Quantization, that sounds complicated.
It's a big word, but the idea is simple. It just means that things like energy don't change smoothly. They can only exist in specific, discrete packets.
So it's stepwise, not continuous, like a switch that clicks into place instead of a smooth dimmer dial.
Perfect analogy. Absolutely perfect. Now, to make this really stick, let's use another analogy. Think of the atom as a highly controlled circular highway system.
Okay, a highway.
The quantum rules are the traffic laws. And these laws are very strict. They say the cars, which are our electrons, can only travel in specific numbered lanes. Lane 1, lane 2, lane 3.
And these lanes are the orbits.
Exactly. And not just that. They can only travel at specific speeds in those specific lanes. A certain speed for lane 1, a different speed for lane 2. And those speeds correspond to specific energy levels. But here's the most important rule. A car, an electron, cannot exist between the lanes. You can't drive halfway between lane 2 and lane 3. It's forbidden.
Okay, that's a strange rule for a highway.
It is. And that brings us to the big why. Why did physicists, specifically Niels Bohr, have to invent such a strange rule that went against all of classical physics? Because classical physics predicted a catastrophe.
A catastrophe.
A universal one. You see, Rutherford's model with the nucleus and orbiting electrons was a huge step forward, but it had a fatal flaw. According to classical electromagnetic theory, a fundamental law of physics, any accelerating charged particle has to radiate energy. It's not optional.
And an electron moving in a circle is accelerating, right? Because its direction is constantly changing.
Precisely. So the orbiting electron should be constantly radiating away its energy. And if it's losing energy, what happens to its orbit?
It would shrink. It would get slower and spiral inwards.
Yes. It would spiral into the nucleus. And the calculations showed this would happen in about 10 to the power of minus 11 seconds.
That's basically instantaneous.
Instantaneous. All atoms everywhere should collapse. The fact that you and I exist, that this table exists, was a complete violation of classical physics.
Wow. Okay. So that's a pretty big flaw.
It's the biggest flaw imaginable. So Bohr's quantization was the solution. It was a radical fix. He just proposed a new rule. In these special allowed orbits, these stationary states, the electron simply does not radiate energy. The classical laws are suspended. Let's build a mental image for this. Forget the highway. Picture a spiral staircase with glowing steps.
Okay, glowing staircase.
The electrons can only exist perched on these steps. They're stable there. They cannot float in the space between the steps.
So when an electron wants to move, say, from step 3 down to step 2, how does it do that without passing through the forbidden space?
That is the quantum weirdness. It doesn't travel through the space. It performs what's called a quantum jump. It's instantaneous.
Yeah.
It's on step 3, and then blink, it's on step 2.
It just disappears and reappears.
In a sense, yes. And when it makes that jump downwards, it releases the energy difference, the height difference between the steps, as a single packet of light, a photon.
And the color of that light depends on how big the jump was.
Now you've got it. A big jump is a high-energy blue photon. A small jump is a low-energy red photon. The yellow sodium light is just one specific jump happening over and over.
So If the electron is on the lowest possible step, the ground state, it can't fall any further.
Exactly. There's no lower step to jump to. It's trapped. That's what makes the atom stable. That lowest step prevents the collapse. Now let's see how our insert textbook formally describes this journey. It's important to know the official language for exams. Can you read what it says about the early models? Let's start with Thompson.
Okay. It says, J.J. Thomson's model, 1898. The positive charge of the atom is uniformly distributed throughout the volume of the atom, and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was picturesquely called plum pudding model of the atom.
Right. A simple idea, but it's proven wrong by Rutherford's experiments. And then came Rutherford's model. What does the text say about that?
It says, Rutherford's model. The entire positive charge and most of the mass of the atom is concentrated in a small volume called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun.
And there it is. That phrase, just as planets revolve around the sun, was the source of the problem. It implied classical rules, which, as we've seen, lead to collapse. So this is where Bohr stepped in. He kept Rutherford's nucleus, but introduced his new quantum rules. His key postulate, the thing that enforces stability, is the quantization of angular momentum.
Right, the formula L equals n times h by 2 pi.
Yes, low dollar and h2 pi. That n can only be an integer 1, 2, 3. No fractions allowed. This mathematically locks the electron into those specific orbits, those specific steps on the staircase. And this directly leads to his third postulate, which is the equation for the light we see. When an electron jumps from a higher energy state, AI, to a lower one, AJ free, the photon's energy is exactly the difference. AI is we'll say 2. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.arhim. Now let's see how powerful this idea was with a quick example. This is how Bohr knew he was onto something huge. Let's take the hydrogen atom. Imagine an electron jumps from the third energy level, n equals 3, down to the second level, n equals 2.
Okay, a one-step jump.
Using Bohr's formulas, you can calculate the exact energy difference for that jump. It turns out to be about 1.89 electron volts.
A very specific number.
A very precise number. Now for the magic. We take that energy value and we use the formula AD-Shekel to calculate the wavelength of the light that should be produced.
So you're predicting the color before you even look.
We are. And when you do the calculation, the wavelength comes out to be approximately 658 nanometers.
And what color is that?
That is red light. Not just any red light. It is the exact wavelength of the famous bright red line in the hydrogen spectrum, the H-alpha line, that scientists had been measuring in labs for decades.
Wow. So his theory, which seemed so arbitrary, predicted the experimental result perfectly.
Perfectly. That was the stunning proof. This strange idea of quantization wasn't just a clever trick to avoid collapse. It was a true description of reality. And, just as a quick connection to our next topic, while Bohr's quantization rule seemed to come out of nowhere, a few years later, a physicist named Louis de Broglie showed it was a natural result of electrons behaving like waves. But that's a story for another time. Okay, now for a very important section. Let's talk about the silent killers, the common mistakes that can cost you marks in the exam. Misconception number 1. Students hear planetary model and think electrons can orbit at any distance like planets can. This is completely wrong.
Right, because of the staircase. The orbits are fixed.
The orbits are fixed. They are quantized. The space in between is forbidden. So the hook to remember is, quantized means stepwise, not smooth. Misconception number 2. Students imagine the electron slowly, gradually spiraling into the nucleus. That's our classical intuition at work.
But we know it doesn't spiral, it jumps.
It jumps instantaneously. It can't spiral because it can't exist between the levels. The remember hook here is more dramatic. Quantization saves atoms. Without it, everything collapses instantly. Your existence is proof of quantum jumps. And the third, and very critical misconception, students think Bohr's model and his formulas work for all atoms. They try to apply it to, say, a carbon atom.
And that doesn't work. Why not?
It only works for hydrogen, and what we call hydrogen-like ions, things like ionized helium, which have only one electron left.
Well, because it's a single electron model, it doesn't account for the repulsion between multiple electrons in a bigger atom.
You got it. That's the key limitation.
Oh.
So I need to remember, Bohr's model is why atoms are stable, but it's limited only to single electron systems because it ignores electron repulsion.
Got it. Stable orbits, but only for one electron.
That distinction is absolutely crucial. Now let's lock this in with some memory aids. First, a simple phrase to repeat to yourself. Atoms are stable because energy is quantized. It comes in packets, not continuously. Second, a physical gesture. Try this while you study. Stand up. Imagine you're on a staircase. Plant your foot firmly on a step. Feel how stable that is.
Okay, yes, solid.
Now, try to plant your foot smoothly in the empty space between two steps.
You can't. You just fall to the next step down.
Exactly, you fall. That's the quantum jump. That physical feeling of stable versus impossible is quantization. And for an extreme association, just remember, without quantization, classical physics says you should not exist. You should have collapsed in a fraction of a second after you were born. The fact that you're here is proof of Bohr's idea. All right, to wrap up our deep dive, let's go over the 3 absolutely essential exam-safe summary points from today. Number 1, the Rutherford nuclear model established that the atom has a tiny, dense, positive nucleus with electrons in mostly empty space around it. Number 2, classical physics predicted this model would be unstable, but Bohr solved this by postulating that angular momentum is quantized, which leads to stable, non-radiating orbits. And finally, number 3, this quantization is the reason atoms have discrete energy levels, and it perfectly explains why they emit unique line spectra, their atomic fingerprints, when electrons jump between these levels. For maximum marks in 12 CBSE Physics, Chemistry, and Maths, visit ProfSam.com. That is PROFSAM, right? Yes, PROFSAM.com. Thank you for joining this deep dive. Study hard and all the best.